Welcome back to Learning with Ms. H. Today we're going to look at absolute rock age dating. We talked about relative rock age dating before, and that's putting everything in a sequence or an order. Absolute rock age dating is going to give us actual numbers. So we're going to do a couple of things today. You're going to read and take notes over the background information. It's a little bit shorter. Then you're going to take notes from the presentation, and then come down here and look at this reading that's linked. You do have a bell work assignment here, so if you come up here to the bell work, you'll see that there is an assignment here. It is for points, so please make sure you do it. It's just going to be a review of absolute and relative dating. You're going to take a look at these questions here, and you are going to answer them based on the images that you find. Do it in a text entry box and get it turned in for points. Once you've done that, you're going to go ahead and do the lesson. There is no other assignment for today's lesson because tomorrow we're going to do a lab activity with this. You do have a little bit of a comparison down here at the bottom that shows relative dating on the left, absolute dating on the right. So relative is just sequence. Absolute gives you the numbers here. So if you are going to go through the notes on your own, you can go ahead and turn the video off at this point. If you want to go through the notes with me, grab your notebooks, pause me while you do that, and then come back. All right, welcome back. Hopefully you got your bell work done, your notebooks here. So let's go through our absolute dating slides. So we have two types, relative and absolute. We've talked through those. Relative is sequence, absolute gives you an age. Remember, when we're going through these, you can always pause the video to finish the slide off and then restart the video to move on. So for absolute dating, the way that this works is we use radioactive isotopes to find the age of rocks and other materials that we can sample. Basically, you have atoms of an element that have different numbers of neutrons, and those are called isotopes. If you look at the periodic table, they're all going to have the same number of protons, but then when you have extra or fewer neutrons, you change the mass, and that's going to make it different from the normally found substance out in the world. So we're going to take a look at those isotopes, those elements that have different numbers of neutrons. And those are going to be radioactive isotopes that we're looking at because radioactive isotopes are going to decay. They're going to push off pieces until they turn into a different element and become stable. So radioactive decay is when you have the original element or parent isotope that is breaking down and expelling particles because it is unstable, and it's going to try and reach a state where it is stable, and that's going to be called the daughter isotope. The amount of time it takes for a sample to lose half of its original parent isotope is called a half-life. So we are going to measure how many half-lives we have in order to find the age of a rock. So if the half-life takes 20 years and we've gone through 4 half-lives, 4 times 20 is 80, so that sample is 80 years old. Here's an example with a picture for you. If we have the image on the left, the green is our parent isotope, the purple is the daughter, so what it's going to turn into. So when the parent isotope loses half of the original parent element and turns into this daughter element, that's 1 half-life that we've gone through here. So we started off with 16 parents, now we have 8 parents and 8 daughters. So we've cut it in half here. Each time that happens, it's another half-life. So if we lose half of the parent again, we'll lose 4 more of these, so we would have 4 parent and 12 daughters. That would be a second half-life. They're depicted in graphs like this, so you can see the radioactive parent isotope is this colored bar here, and then this black and white section is the more stable daughter isotope that it's going to turn into. Each time we go through a half-life, we lose half of the parent. So we start off with 100% parent. When we get to 50% parent, that's 1 half-life. For this particular element, if you look down here on the time, it takes 5 years for that to happen. So every 5 years, you lose half of your parent sample, and it turns into daughter sample. So in 10 years, we've lost half of what was left. So now we've gone 100 to 50, and now we go 50 to 25. If we go another 5 years, we're going to lose half of that 25. So now we're at 12 and a half. And it's going to keep going until there's nothing left. You need to be able to read charts like this. There are a couple of those on the test. So typically for radiometric dating, we need them to be igneous rocks. When they form, the minerals in them are only the parent isotope. They generally don't have any of the daughter isotope present when they form. That makes it a lot easier to determine what the half-life is because we know we had a pure sample to start. Here's another example of a chart that you might see on the exam. You have 100% red dots for the parent, and then after one half-life, you're half and half, 50 parent, 50 daughter. After a second half-life, you're 25% parent, 75% daughter. Third half-life, you go down to 12.5% parent, and so on. Some of the methods that they use for radiometric dating, they're going to use different isotopes of different elements. Some of those elements are more radioactive than others, and you have to be in the window of that half-life range in order to complete this. If the sample size is too old, then it's had all of the daughter isotopes replace all of the parent isotopes, and it's hard to tell how long it's been sitting there with all daughter isotopes. If it's too young, then it may still have all of the parent isotope and none of the daughter isotope. So there's a sweet spot for the age range, and that's different for each element that you try to look at for radiometric dating. When we talk about radiocarbon dating, that's going to be organisms that are organic. So something organic like wood, bones, shells, anything that was alive at one point. If it contained carbon, we can do radiocarbon dating. So once the organism dies, it's no longer taking in carbon from the environment. So when this carbon degrades, more gets taken in and replaces it. Once it dies, that process stops happening. So then when that degradation happens, and you have radioactive decay, then you start losing the carbon. And that's why this works so well. So the half-life of carbon-14 is 5,730 years. So the number of half-lives of carbon-14 that have passed by gives us our absolute age. So we would take 5,730 years times the number of half-lives that we've gone through. We can only use this for organisms that were organic, that contained carbon. Basically, we're going to use this for things that lived in the last 45,000 years. Anything older than that is outside of our sweet spot range. We can also use several other radioactive elements, and here's a list of those and the age ranges of when you would use them. I would go ahead and jot these down so that you know what they are. Some of these are on the test. Here is another table that you need to be able to interpret. Carbon is red, nitrogen is blue. So in this sample, we started off 100% carbon, and then each half-life we lose half. So what you're looking at here is radioactive decay of carbon into nitrogen. So our carbon is turning into nitrogen. The parent is carbon, daughter is nitrogen. We've gone through 1, 2, 3, 4 half-lives here. So on this, you'll see questions like, how many half-lives have we gone through in order to get 70% nitrogen? It might ask, how many years have gone by after 3 half-lives? It might ask, how many years have gone by after 6 half-lives. We only see 5 here. We only see 4 here, actually. 1, 2, 3, 4. So in order to get to half-life 6, you would have to add 5730 onto this number again. So 22,920 plus 5,730, and you would add that 5730 twice to get to the 6. So it may ask you to extrapolate and extend the graph out. You might have an image like this where it has missing information, and you would have to fill in the blanks for the missing information or answer questions about this. So this is percent of parent, percent of daughter, number of half-lives. So at 0 half-lives, it's 100% parent. Our fraction is 1/1, so it is completely parent. And our ratio is 1 to 0. So then it asks at the second half-life, it might ask, how much of the parent do you have? 25. How much of the daughter? 75. What's the fraction of parent? 25 plus 75 is 100. So 25 is 1/4 of 100. Okay. 75 is 3/4 of 100. Your ratio would be 1 to 3 because 25 goes into 75 3 times. So you need to be able to answer questions based on this type of graph as well, or this type of table as well. Again, tables with missing information, answer the questions on it. I'm going to let you go through all these practice questions on your own here. The answers are listed. There's more graphs for you to practice working with. So go through these and answer those questions. Pause me while you do that and then come back. Radioactive or radiometric dating is used as far back as 4.5 billion years. It was how we determined the age of the solar system by looking at those meteorites that first landed on Earth. We don't use it in sedimentary rock. Those fossils can't be dated directly. We have to put them basically in a time frame based on the rocks around them. So we'll date the rocks around them, and then everything in those rocks that's fossils is going to be around the same time. We talked about index fossils. So that's going to be anytime you have a fossil in more than one location in the same rock layer, that's always going to be the same time frame, no matter where it is on Earth. So it has to be a common fossil over a large area, and it had to have lived in a short geologic time frame, and it has to be unique in some way. They're going to be markers for when organisms were alive on Earth, and they can also be used to date rocks in separate areas. If you have an index fossil from an area that you know the time frame, if you find that fossil somewhere else, you know that that's going to be the same time frame. So that is the end of the notes for today. Go ahead and go through and read your relative age dating text, and then you are done for the day. I will see you next time.